All right, so let me see how this works. Switch account, YouTube Studio, content maybe, live. Okay, this is live, details. How do I get the chat? Good day. Hi. All right, let's get started. So I can see the chat. So hello chat. All right. So if you can hear me, just let me know. Okay, let's go. So today I have a couple of things to talk about. It's mainly, well, okay, hold on. I have an echo. I guess. All right, so there you go. So I have a couple of things to talk about. The mainly is about the proof of balance thing. But I wanted to use this opportunity to also talk about the protocol itself, so that there's some context. So the proposal proof of balance is can be used for showing that you have a particular amount of coins under your control, and this can be used to either just show that you have a certain balance, but also because we can associate some encrypted content with that proof of balance, you can use that to vote for a particular election, or to include an address so that you receive an airdrop based on how much ZEC you have. And this stuff is going to be completely shielded if you use Orchard. So normally you can use also the main proposal I have was about transparent sapling and Orchard. This one today is just Orchard because it's heavily inspired by the the proposal from the ECC engineers, Dera and Strad. The main issue that we have in my proposal was that you are also revealing the nullifier, and by doing so, if you are making simultaneous votes, you will have the issue of having easy correlation between your votes. So if that's not clear, I think that we can rewind a little bit and talk about what needs to be done for this proof of balance. So when you want to prove that you have certain amount of coins, you have basically to show 5 things. You have to show that the coins exist, that you're not using some node that never existed, that you are that you're not making them up. So that's criteria number 1. The node was created at some point in the past. Second thing is that node was not used before, so it's not already used. The third thing is that the node was not used to in the proof of balance, right? So the node not used is the not being spent. It should not be spent, but it should also not be already reported. So unspent and unreported is similar concepts, but it's not exactly the same, because we basically have the idea that um, we have nodes in the main Zcash chain that can be traded. But when you are creating this proof of balance, you're moving to a alternate universe in a sense, where you're showing coins and you don't want to be using the same coins twice for voting. So one thing is about not spending the same stuff twice, and the second thing is not voting twice with the same coins. So same idea, but not exactly the same implementation. So that's number 3. Number 4 will be that well, you have authority to spend them, right? You have ownership of these coins. And finally, that the amount that you are reporting is correct. You're not over-reporting coins or under-reporting coins. And all this stuff has to be done in a cryptographic way. If we were doing with transparent coins, it would be fairly easy because you could go to the blockchain, look at the particular node, and see the entire history and track whether they were spent or they were reported before. So this would be very easy to do if it was Bitcoin. But Zcash, if we're using shielded coins, then clearly that's not possible because only the receiver and the sender are knowledgeable about what the node is. For the rest of the world, so including the guy who's doing the election, the guy who's running the election, they have no idea of exactly what the node contains. So you can't really use anything about the encrypted node. You have to work only with the node commitments and in the nullifiers. So what do we have, right? We have in the protocol, we have stuff that we play the role of making the system consistent in the 5 aspects that I mentioned, and all these 5 things have to be proven in the in zero knowledge in the proof that you are creating and you are giving to the election board. Let's see how this is done in practice. In practice, I have a setup here. Do you see actually? Does it change? It doesn't seem to change. I tap stuff, but oh, let me see. My phone is. Does the content of the window change? Oh, there's a delay. Okay, there's a delay. All right, so I think it changes, but just a little bit later. All right, so here I have a setup where I essentially have a directory for the guys who are running the election. So I call it the poller, and another directory for the guy who's going to vote. And the poller has defines the election parameters. So he would have a file like this, which gives the URL where that's the website of the entity who's running the election. So in this case, it's election.meteor.cc. Then the name of the particular election or balance that he's doing, and then some heights. The first height is the start height of the election, and the end height will be called the snapshot height. So the to vote, you vote with the coins that you have acquired between the start and the snapshot. If you have acquired coins after the snapshot, then they are not eligible. And if you have acquired them before the start, it's not eligible. Of course, the start can be chosen to be the activation height of Zcash, so very far in the past. But if you choose a more recent period, then you can omit the period where we had spam, and then it reduces the amount of data that voters have to download. So for the sake of this demo, I chose a start height that is fairly recent, so I don't have to download a lot of data. Of course, the coins must be yours during that period, and also they must not be spent. Then you have lockdown and closing. It's for the administration. The idea here is that we don't close the election immediately, and we have some kind of grace period so that if you have a voter that is running a bit late, then he still has a chance to submit their proofs. But that doesn't really change anything about the logistics of I mean the creation of the proof itself. The important period is between the start and the snapshot. So okay, so this is a poller, and the poller has an identity, right? So to create the identity, you use OpenSSL. OpenSSL with the this curve, right? So I can put it as, for example, this guy is a poller, so I will choose poller.pem. And the voter is, for the moment, we don't have the key of the voter. So this identity is because whenever the election board receives a vote, they want to give a receipt back. That receipt has to be signed by the election committee. Right. Let me see if there's any questions on what's going on. Okay. Oh, okay. All right. What else do we have? Data. We have nothing in data. Actually, the poller doesn't need anything. DB, we should have nothing in DB as well. Well, we have just a database. I can delete that guy. And PoB, we have no proof at the moment, so I delete that guy too. So that should be the state of the election board when it starts. So the election board starts. The app, and then it loads his identity. So identity will be poller.pem, and then what can it do now? Okay, it can download the data. So download the data from one of the light wallet D. So I can use this one, for example, 9067. We wait a little bit, or shouldn't be too long because the range is very short. Okay, and now we build the reference data. So technically, this stuff does not have to be done by the poller, but since they are organizing the election, they probably want to do this stuff. All right, because it calculates the root of the both trees, the commitment trees for the nodes, and the nullifier tree. So these values here, they are important because they are parameters to the election. If you look at the election terminal, you see at the end you have these two guys here. They are related to the range of nodes that or blocks that we are running the election over. So if you change anything, if you change the snapshot height or you change the start height, you would have a different range of commitments of nodes that are eligible. So these hashes will be different, and we include that into the election.toml so that the voter can verify that everything is okay, that the software that he is running is also committing on the same routes. So now I go to the voter. The voter has received the same file, right? So the election file is the same. And in practice, he should download that from the website of the election committee. Right? So he downloads the same file. And he has a database file, PoB.db, probably not needed. Voter, yeah, I surely need that. So I delete the PoB.db from the voter, but you should have the zec.db. So the zec.db is the wallet file. That's the database file that you get from wallet. This is so this is what your coins are going to be recorded. All right. What else do we need? We need an identity as a voter because we are going to encrypt our vote. The idea here is that the committee will first receive our vote, and we'll first verify that we are in control of these coins. But the vote itself is encrypted. So they receive all the votes, and until the closing height, they don't know what you voted for, right? They cannot open the votes. Once all the votes have been received and the election is closed, then they can open the ballots, right? So as the voter, you will encrypt your message with your own key, right? So I need to generate my key as well. So it's the same command, but this time it's the voter.pm. All right. Then what else? The PoB I shouldn't have, and the data I shouldn't have at this point either. All right. So then that is my setup. So I start the vote app, which is actually the same app. Just rename the exec. I load my identity, but this time I'm the voter, so I'm going to be this identity. I'm also going to download the same data. So I'm going to download from another server. Just because why not? And this time I need to build the reference data. Right, building the reference data is necessary for creating the ZK proof. ZKP. All right, so the values that I have here, they must match the stuff from the election parameters. So let me check, and yeah, they check. They are the same. So my reference data is correct. Right. So now I can restart this app, and I can I have to reload my identity, and I can create the proof. So I create the proof, give a file name. I give the account number because my wallet can have multiple accounts, and I give the message, some message I want to add to my vote. So I would say Bob because I'm voting for Bob, and this gonna create a few things. It's gonna create the ZK proof for the proof of balance statement, and it's gonna also create the encrypted message. So at this point, I'm done. I have a vote inside this file. It's a 5K binary proof, and submit it to the election board. So to submit it, normally you can upload it, but in this example, I'm just going to copy the file to the other guy, Porter. So I'll copy it to the Porter. And now I go to the Porter. The Porter has received my file, pob.bin, and now he needs to verify that this file is correct. So he starts the app, and then he loads his identity because he wants to verify and give me the receipt. Right, so I need still the Porter identity, and then I say verify proof, pob.bin. So this will check the, I have to init the database, initialize database, and verify the proof. All right, so it has verified the ZK proof. It has verified that the signature, the note was signed properly. So the voter has spending authority, and that the binding signature on the value is also correct. So it has verified that the note exists. It has not been spent. It has not been sent to us before, because now if I verify a second time, this PoB has already been submitted to us. So you will report that we have a double report, right? It says duplicate proof. It means that we have already received this guy, so it doesn't count. Then the fourth thing was that we had spending authority. So that's the spending signature. and that the value matches. So that's the binding signature. So we have verified the 5 things, and we have accepted this vote. But at this point, we cannot see what the vote is. So technically, normally you have to wait for the collection of every vote. And let's assume now that it's over. We have reached the end of the election period. So at this time, we are back to the voter has to submit his secret key so that we can open the vote. So I'll copy the voter PM to the poller. So obviously, you every time you vote, you have to use a different identity. Yeah, but you can use the same coins. You have to create different PEM, different signing encryption keys. Then I go to the poller and I start the poller software again. This time, since I want to open the vote, I have to load the identity of the voter. And then I can open the proof. Open what proof? Open the proof that I received earlier, the PoB.bin. Yeah, that should be it. And the message is now decrypted, and it says Bob. So the vote is for Bob. Right. So that concludes the demo. We have gone through the entire workflow. So the question here is that is there size constraints? So that's a very good question. The size constraint is actually indicated in the election.toml. So in this particular toml, you set the board sets the maximum size, and I set it to 64. If a vote is sent with a message larger than 64, then it will be rejected. So it is up to the particular election board to decide the format and to decide the size of the message. It's not really it's not enforced really in the protocol. It's just a decision. So, for example, if you have an election for just one person, you can have a counter that says candidate 1, candidate 2, candidate 3, right? So it could be an integer. If you want to have a write-in election, then you can put a text field for the name of that person. If you want to do an airdrop, then it would be the length of an address. So it doesn't really. It's quite flexible, right? Because the election software doesn't care really about what you put inside. It will just make sure that the size matches is maximum the size that you have in the definition. Okay, so okay, so that's the demo. Again, the way it works is, I think it's the part that makes it interesting from the protocol point of view, from the Zcash point of view, is that if you have different elections and you use the same coins, you will reveal different nullifiers because each election would have a different. We hash basically the definition of the election, right? The URL, the name, the height, all these guys are hashed together, and then it creates a value that is fairly unique. And for the same coins, they would have different nullifiers for different elections. So you don't have to move your coins. You can revote with the same coins all the time, because the recipient will not be able to link these particular choices. At the end of the election, the votes can be open. The election board can reveal everything, and it can show the votes like Bob, Joe, whatever, right? And you can also show the nullifiers used, but these nullifiers will be scoped for a particular election. So yeah, it's not possible to say that the same person has voted for Bob in one election and for Joe in the other election. The second other thing that is pretty interesting is that since the calculation of the weight is in a circuit, in a Halo 2 circuit, you can also imagine that you don't have to have one-to-one mapping between the coin balance and the weight of your vote. You could have like quadratic, or you could have weighted by age if you want. Right? You have to change the formula. I think quadratic is not a very good idea because of severe attacks, but weighted by age is should be fine. I mean, it doesn't really matter in the terms of implementation, but just that if you do a quadratic, I think it gives it's very easy to game the election by splitting your coins into different accounts. Right, you vote multiple times and you have a better outcome. Then other things that you can do. Oh yeah, the other thing is that when you submit the votes and the election board receives them, so most of the stuff that they will receive is one ZKP, one domain nullifier. So the domain nullifier serves as the unique ID of that particular node, and then it has a hidden value, right? The hidden value is you can't open that value. It's encrypted as well. So if you have, for example, 10 nodes, you would receive like 10 ZKPs, 10 nullifiers, and then 10 encrypted values. And if somebody reuses one of the nullifier, then the entire vote is cancelled. Right? The second time, we check that all the nullifiers are new. So the voting software will make sure that you don't do that. But if you want to attack, and then it will be caught by the election board. Right? And the one thing that is unclear is the total value of these nodes. And I think this is a pretty cool thing, because by publishing the entire the total value, you can have a counter that says, "Oh, this our election is popular," and you can have a running counter of how many coins were submitted while the election is running. And at that point, you still can't know who's winning, right? Because the messages themselves are encrypted. You just have an idea of the participation rate, if you want. So this is kind of like when you have a re-election and the polling guys are saying, "Oh, we have a high participation rate today or not," right? So you can measure that, and that's the only thing really that is unclear. Or everything else is encrypted. What else can we say? Yeah, I think that's it. That's all I have for this presentation. If you have questions, then reading the chat. Yeah, pretty fast actually. If you want to see something else again, you can also do that. Okay, thanks. Yeah. Other than that, I think that's it. Yeah, it's end to end. So are we good? If we are no question, then I think we can stop. Oh, well. So the results can be verified. The results can be verified by everyone. So at the end of the election, what the idea is that you will reveal all the I didn't talk about this, right? So the workflow is that the election starts. the voters download the election.toml, so they have the stuff, the parameters. They create their own keys for this particular election. They submit their vote, and the election board returns the receipt. Right, the receipt is actually signed. Is a signature on the hash of the vote. So at that point, if if the voter doesn't see his vote on the official board, then he can say something went wrong, and he can submit a complaint that his vote should be out there. Right? So that's why we have a grace period at the end, where there's the locking period where you're not supposed to submit any vote anymore, but you can monitor that your vote has been accounted for. Right? And if you don't see your vote, then you go to the forum and you complain. Right? At the closing time, then it's like the roulette. Everything is closed. You cannot do anything, and the and all the voters have to submit their secret keys so that we can open the board can open the votes and tally the results. And then at the end, they will submit. They would publish all the ballots with all the keys, so that anybody with this software or some similar software can do the count themselves. Right? Just run the same stuff. Really, the election board has no particular authority besides the ability to sign the receipts. Right, that's all it has really. Even the verification of the ballot can be done by anyone as long as they have the ballot. So I'm not sure if the election board will publish the entire ballot on their website when the election is still running, but definitely at the end of the election, they should publish everything, all the data they have collected. Then it's their problem. If they don't submit their keys, then we cannot decrypt, and the vote will be cancelled. Okay, so what else do we have? So one thing I want to say is that technically you could do the same thing with sapling. The reason why it's much more complicated to do. I mean, I don't know if it's much more complicated, but I think it's more complicated to do with sapling is because you would need to do another circuit for sapling, and you would have to you would have to do another ceremony to make the to make the trusted setup. Or you can try to do the I mean, it's technically possible to re-implement the sapling logic on top of Orchard, but that's I think nobody has really done that. And in any case, if we want to have this nullifier, so the main reason why you want to do this instead of doing the other solution is because of the nullifier domain thing, right? The one with using the same nullifier as the nullifier from the main chain has some several advantages. It has the advantage that it's all the security proofs have been made, right? So for this one, we still have to go through security reviews and cryptographic reviews and all that stuff, right? For the one, if you use the nullifier from the main chain, then you essentially use the same technology that has already been used in Zcash for years and years and years. So it's very, very robust. And you don't have to do a port to Orchard, right? You can, everything is possible in. I mean, you can use nullifiers from sapling, nullifiers from Orchard, and you can also use transparent funds as, of course. But if you want to have something that is going to be future proof, but require more work to implement and to validate, then I think this Orchard solution is preferable because you don't have to worry about anything. The proof that you're making is not going to be usable anywhere else, and you're not revealing anything. You don't even reveal the nullifier from the Zcash chain. So everything that you reveal here is going to be only usable in that particular election for that particular proof of balance election. Even if you have another one, it's a different domain. Okay. Where netted scheme? Yeah, I don't really think Frost would really bring anything, unless right? Unless no, because it's not. It's it would bring something if you're talking about signing coins that are multi-sig. Basically, the coins that you have that you want to prove, you don't really have authority on them. It's a group of people who have authority to spend them, right? In this case, we can adapt the protocol to accept surely accept signatures that come from Frost. Really, it doesn't change really the PoB protocol, because the signature that we apply on the proof is the same as the one that is applied on spend, except that the Zcash is different. You're not signing on the same content. You obviously don't want to sign on the same content, because otherwise that signature would be usable on the main chain, and you clearly don't want to do that. So we make sure that the SIG hash is different, completely different. But the signature algorithm is the same as the one that Zcash uses, right? So you can use Frost if you want. The only thing that changes is that you're signing on a different hash. Yeah. Okay. All right. If you don't have more questions, then I think we can stop here. Fairly short meeting. All right. Okay. 3, 2, 1, 0. Okay. All right. Thank you. Thank you for attending. Thanks for attending, and the video will be available online on YouTube. All right. So see you around. How do I stop?